teaching diffusion large language models to correct its own mistakes. During training of diffusion models that generate text, there is a ground truth sentence. A brown dog is chasing a red bull. And then some of those tokens are replaced with mask token. And the model needs to demask, revert back, predict the actual token. For example, here, a mask dog is mask, a red mask. So it needs to predict these words. And that's how it learns the language. The problem here is it's always predicting with the perfect ground truth correct tokens. So during training, it's predicting from these ground truth tokens that were correct, that were human data. But during inference, later generation, it's actually generating all of these tokens step by step. In first step, it generates some. In next step, it generates some. But it's then predicting from its own generated tokens, not from the ground truth, always correct tokens. And its own generated tokens can be wrong and bad and incorrect. So during inference, it's predicting from its own past generated tokens, and during training, it's predicting from the perfect ground truth. So it doesn't learn to deal with mistakes in the context that it may generate. This can cause error cascade because one wrong token, one wrong assumption will now condition other tokens, and they will be based on this one wrong token, which will cause the other tokens to be wrong as well, that are generated based on that token, based on that context. This can cause incoherent, repetitive, factually incorrect or hallucinated text. So the solution of this paper is to teach the model to refine its own text, its own generated tokens. So now, instead of training being just generate these mask tokens, there are two stages of training instead. First, they're gonna corrupt the correct ground truth. They're gonna corrupt with some mistakes. They're gonna add mistakes to the good text and teach the model to fix those mistakes, to find badly generated tokens and fix them. So now the new skill that it's learning is not just predicting the mask tokens, but also correcting wrong tokens. And the training data here is text that contains both mask tokens and wrong tokens that are just polluted by the researchers, replaced by the researchers. They create this data by randomly replacing a correct token with another token from the vocabulary, changing a beautiful sunset to a banana sunset. And so these models are vision language models, so they also see images. You can add images to them. So if image shows a cat, they can replace text description or with the answer to some question as this shows a beautiful dog. Let's see an example. So it says a picture of a brown dog sleeping on a green rug. And ground truth captions are a brown dog is sleeping on a green rug. So after masking, a few of the words will be replaced with mask token. And in step 2, they will replace the remaining unmasked tokens with some random tokens, like dog replaced with a car. And so the new sentence could be a mask, car is mask on a blue mask. And the model's goal is to now predict the ground truth sentence by predicting mask and fixing the wrong tokens. So the architecture of the model is the vision transformer for the vision encoder, like Clip's vision transformer. It's gonna divide images into 16 by 16 pixels. But I think the paper doesn't tell explicitly which vision encoder it's using. And for language generation, it's using just diffusion transformer. And then there is a layer that's connecting, that's translating the vision encoding, vision vector embeddings, patch embeddings to language embeddings, token embeddings. Because vision encodings speak the different language, let's say, than the token embeddings. So a linear layer is translating this token to these tokens that can be understood. And they are also different models, so of course they will speak different language, have different meanings for different numbers, different features, different dimensions in the vector. So this error correction and demasking is just the first part. So it learns how to correct errors as a baseline, but every model, depending on its training and architecture, will have its own type of errors it creates. So in the second stage, we will teach it to fix its own created errors. So it may not learn from these synthetic errors from the first stage to fix the type of errors it's inherently producing. So the goal of stage 2 is to fix its own intrinsic mistakes. So this is how we generate data for the second stage. We take the model from the first stage. It's called Rediff base. That's what they call it. And we give it some images and tell it to generate captions or descriptions of those images. And researchers tried different speeds of generating tokens, like 1, 4, or 8 tokens per second. If you are trying to demask more tokens per second parallelly, then there will be more mistakes. The way I understand it is it's then less compute per token. So less compute, less thinking, let's say, more mistakes. And here I'm just talking about turning mask tokens into descriptions of the images. And then they use a more powerful model, which is maybe some autoregressive model like O4 mini. And they give it image, the flawed draft, and possibly optionally the original ground truth of the caption, of description of the image for reference. And they tell it just to fix mistakes in the flawed draft. So to make minimal changes just to fix mistakes. And so this is gonna create new type of training data where the input is the flawed draft and target is the corrected sentences, corrected data, corrected draft. Remember that the model with its attention mechanism sees the image and sees the draft. And it can pay attention to parts of the image and sees that this is a cat, but the draft says, the sentence description says dog. So with its attention mechanism, it can spot these mistakes. So the way it works is image is divided into tokens, and then text is also tokenized and converted into embeddings, all of them. And they're all of the embeddings are concatenated into a single context or sequence. And so if a token says trunk, but it should be bus, because on the image says and the rest of the sentence says it should be bus, then this attention will mix up this information of the bus and the trunk into the trunk token embedding. So there will be this tension or ambiguity. Like this has elements of being a bus token, but it's a trunk token. So the model will eventually learn to turn token trunk directly into token bus without remasking. And that's how the loss function is also structured, to measure if this is bus token. So that's gonna be it for this video. Join my school community to become AI researcher and see you next time. Link below the video.